Section 10.5 deals with the binomial theorem. And the binomial theorem deals with this concept of expanding out binomials. We've seen things like x plus 4 squared, and we know that that translates to x plus 4 times x plus 4. Or we can look at, x plus 2 to the third power, and that's x plus 2 times x plus 2 times x plus 2. But the binomial theorem deals with a concept of expanding these out, like to the 5th power, 6th power, 7th power, without having to actually just do x plus 5 times x plus 5 times x plus 5, 6 or 7 times. So there are some formulas that we have that go behind this idea of the binomial theorem. Before we can actually just jump into the theorem, there's a few things that we have to go back and look at. And first thing is, we're going to look at a special notation that will be new to anything or different than anything we've seen in this course in particular, but it's something that's called factorials. Now, we have a definition here of a binomial coefficient, and you have in parentheses this n and this r, and of course that is read n above r, and what we're looking at is this notation here, that's n above r. And this is called a binomial coefficient, and what this actually means is this is n factorial. That's that word that I said that's going to be kind of some new symbols and new notations that you're going to see. And the definition of this binomial coefficient is n factorial divided by r factorial times n minus r factorial. Sometimes you will see the notation, this NCR, instead of the n above r notation. But for what we're going to use and what we're going to see in this section is we're going to see the n above r notation. But let's first understand what this idea of a factorial means. Products of consecutive positive integers occur quite often in sequences. These products can be expressed in this notation that we're talking about, factorial notation. If n is a positive integer, the notation, this n with this exclamation mark, is read n factorial. It's the product of all the positive integers from that number, from n down to 1. So, for instance, of course, except for the 0 factorial, by definition, the 0 factorial is just 1. That's kind of a special case. But what I mean is, for instance, 3 factorial, that's 3 times 2 times 1. 4 factorial starts at 4 and goes down to 1. So 4 times 3 times 2 times 1. 5 is 5 times 4 times 3 times 2 times 1. So that's the idea of what we mean factorial. So when you see that exclamation mark, say, 7 with an exclamation, that's 7 times 6 times 5 times 4 all the way back down to 1. So that's the definition of what it means to be a factorial. Okay, so again, before we actually get into the binomial theorem and the expansion that we're going to look at, let's first know how to use the binomial coefficient notation, because you're going to have to understand this idea, and you're going to have to understand the idea of factorials to be able to work through some of these as well. So we'll go through just a couple of these, starting with example A here, which is n above r. So in other words, this is 6 and 2, and just to kind of label everything, the n is the 6 and the r is the 2. Now again, this formula, since this is n above r, the formula that was given to us above is n factorial, which is the numerator, over r factorial. So n factorial over the r factorial times the n minus the r factorial. So all we have to do is plug this in, and we can simplify fairly easily on some of these, but this is going to be 6 factorial over 2 factorial times 6 minus 2 factorial, which is actually just going to be 6 factorial over 2 factorial times 4 factorial. Now, like I said, there are some shortcuts we can use. But just to kind of show you the long way through this, this is going to be numerator 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1, and then times 4 factorial, which is 4 times 3 times 2 times 1. So reducing everything that we can, of course, the 1's cancel, the 2's, the 3's, the 4's, and basically you could go ahead and reduce that 6 and the 2, but that does leave us with just a 30 over 2, which actually just equals to 15. So n above r is actually just equal to 15. Alright, so example B is n above r, so we have on this one 9 and 3. So labeling, this is my n, this is my r. Again, the formula is n factorial over r factorial times n minus r factorial. Plugging in my numbers here would give me 9 factorial over 3 factorial times 9 minus 3 factorial. So basically what we're looking at here is going to be 9 factorial over 3 factorial times 6 factorial. Now, instead of having to expand this all the way out, if I start with the numerator and say, okay, well, 9 factorial is 9 times 8 times 7, and then when I get to the 6, if I write this as 6 factorial, that means that that's going to be 6 times 5 times 4 times 3 times 2 times 1. So because I have a 6 factorial in my denominator, we don't have to actually write all of that out. There are shortcuts still to using this factorial. And then, of course, the 3 factorial is 3 times 2 times 1. And since, again, I can see that 6 factorial is just 6 times 5 times 4 times 3 all the way down to 1, I also noticed that in my numerator, so I was able to stop and not have to physically write all that out just to go back and then just cancel it out. So using that method, I can say, well, that cancels out there, which is going to leave me with just 9 times 8 times 7 in my numerator is going to give me 504 in my numerator over 6 in my denominator, and that just gives me, when I reduce that or divide that, an answer of 84. Okay, so it's important to understand how the factorial works and then how this binomial coefficient works, and when you see this notation. Alright, so now we're ready to talk about this binomial theorem. And the binomial theorem, again, deals with what I mentioned previously as you have x plus 2 squared or x plus 3 to the 5th power and things like that. And usually we don't have to expand out anything much more than just the FOIL method. We know how to do that. There may be a few times where we've had to maybe do a cubed. But the binomial theorem allows us to basically have a shortcut. And you can start seeing that patterns appear. A plus b to the 1st power we know is just a plus b. If you square it, and you'll notice the pattern here, if we square that a plus b, we start out with a to the 1st, and then we square it, so it starts a squared, we cube it, becomes a cubed, a to the 4th, a to the 5th. And then look at the last terms. The last term starts out as the b, and then the last term squared, since it's squared, and then the last term cubed, since it's cubed, and then the 4th and 5th, and things like that. And then from there, we have a pattern. It almost starts building like a little triangle here of this expansion. And, you know, one thing that you can kind of see in some of the patterns, and you can look over this and see if you can see the patterns, but like here we have a plus b, and then in the middle we have the a and the b. You know, next we have the a squared, and then the a squared moves here, and then times the b. And then down, you know, goes from a squared, a cubed, a to the 4th, and then, you know, you can kind of, there's lots of patterns you can go through, and I'm not going to go through and, you know, pick out all these patterns for you, because you can look at them and see what's happening as we grow each step by step. You know, the coefficients here go 2, 3, 4, 5. So you can kind of look over that and, you know, kind of develop these patterns yourself. So each expanded form of the binomial expression is another polynomial. You're taking a polynomial and you're expanding it out, and it stays a polynomial. And again, here you can read through that. This is just out of your textbook and what I've just kind of gone through and explained here. But there are the patterns that you can observe that we basically just talked about. Now, here is the formula for expanding binomials. So instead of us having to take, for instance, a to the 5th and go a or a plus b to the fifth. Instead of taking a plus b times a plus b and fooling two of them out, and then taking that answer and fooling it with another one, and just doing this non-stop FOIL process, we can use this idea here. And if you have a binomial that's raised to a power, then this is just equal to, and the formula, I know it doesn't really make a whole lot of sense. It looks like there's a lot of symbols and a lot going on, but basically all this comes down to is this is what it's actually equal to. This little symbol here that you see, this is actually a symbol for summation. That's all that means, is a summation, which just means you're adding up all of these. And that's because it's coming from add this, plus this, plus this, plus this. So we kind of just get right down to this is what it's equal to. Now, to understand this, because again, these are a lot of new symbols that we've never seen before. Well, first of all, this is just n, and this is just r equals 0. These are called your lower bound and your upper bound. Lower being the bottom and n being the top, but it's taking from r equals 0 up into n. We're summing everything from where my r equals 0 to my n, whatever my n is, whatever my n, which is your exponent. And it's just a process of taking all of these binomial coefficients and applying it to the formula, and then doing starting with 0, and then summing that, and then summing it at 1, and then summing it at 2, and 3, and 4, and 5. So we kind of break it down to just this formula here that we have highlighted. So again, it's one of those things that it's easier to just kind of see it put into an example and see the formula applied versus trying to understand what this definition is saying. Okay, but basically it just comes down to a summation. We're going to sum up all these kind of binomial coefficients that we have. Alright, so let me show you how to apply this to an example. Now, one way to expand this is to say, well, this is x plus 2 times x plus 2 4 times. And you could FOIL that out, and then you could FOIL it out again. And that is one option you have, but that's not necessarily the best option. Now, there are actually 3 ways technically you can do this. You can do it that way and just FOIL everything out. Or, back over here, I showed you that here are the formulas for the first 5. So you can use the formula. So in this one we're in a to the 4th. So the formula here for, if you have a binomial to the 4th power, according to the chart on the previous slide, the formula is this is an a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed, and then plus b to the 4th. Now again, that's coming straight from the formulas that we have over here, and it's okay to use those, if you wanted to memorize those. So we have a to the 4th, a plus b to the 4th, which is a to the 4th, plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. And from here, it's just a matter of saying, well, my x is representative of the a, my b in the formula is the 2, and all that's going to be is just plugging in for your a and your b. So, and let me reverse this so that I have it set up exactly right. So all you're going to do is in your formula plug in for a, and then everywhere there's an a, put an x, everywhere there's a b, put a 2. Okay? So this is the same thing. X plus 2 to the 4th power would be x to the 4th plus 4 times a, which is x cubed, times b, which of course would be, that's where my 2 comes in, because b is 2, plus 6 times a squared, so x squared, times b squared, which is 2 squared, plus 4 times a times b cubed, and then plus, you take your b and you raise it to the 4th power. So, knowing the formula, we don't have to FOIL anything out. This is just going to be x to the 4th plus 8 x cubed plus, of course, 2 squared we know is going to be 4, so it's going to give me 24 x squared plus 2 cubed is 8, so plus 32x. And then, of course, plus my 16, because 2 to the 4th power, 2 times 2 times 2 times 2. And that is what x plus 2 to the 4th power is without having to FOIL all of that out, FOIL these two together, and then take those two answers and multiply them together. We just have a definition. Now, the other thing that I showed you, and I'm going to show you both ways. That's the second way you can do it, other than just absolutely just fooling everything out. But the formula that we had was from the previous definition, using the binomial coefficient idea, that if you have a binomial to a certain power, you can do the binomial coefficient times a to the n minus r power times b to the r power. Now, how we know what is what? Well, first of all, we know that the n on this one, for instance, this is going to be x plus 2, and this is to the 4th power. So labeling everything is important too. My n here, of course, is going to be 4. The a is equal to x. The b is equal to 2. Now, where the r comes in, and how this r works, is if we go back and now, like I said earlier, it's sometimes easier to look at the problem and then kind of understand how the formula is working. If you look at the object here of the r, it starts 0, 1, 2, 3, and it goes on for however many n's that you have. So we don't actually have an r. R starts at 0, and then it goes to 1, and 2, and 3, and 4, because we're summing everything up from 0 on up to whatever n is going to be. So you start with n, which is 4. R starts at 0 to the a, n minus r power times the b to the r power. And then plus. The next one is n is still 4. The only thing that's going to change is your r every time. So now we go to 1. So this will be x to the 4 minus 1, b to the first. And then plus. And of course I'm going to have to go to a new line here. Plus 4. And r goes to 2 now. X to the 4 minus 2 this time. And then 2 to the 2nd power. All that's changing in each sequence here is the r. And we know when to stop when we get to 4. Because when r and n are equal, that's when we stop. So this will be 4, 3, and then x to the 4 minus 3, b, which is 2, to the 3rd. Let me change that. Left that as b, didn't plug in my 2. And then plus, the next sequence, or the last, will be 4 to 4, x to the 4 minus 4, b to the 4th. So, you know, some people say, okay, well, is this really a shortcut? Not necessarily always a shortcut. Now, the formula, or knowing the pattern, is where we actually get our shortcut. But still, we do have alternative methods for working this out. So we've got this x plus 2 to the 4th power is equal to. Now, starting here, n above r, so we have 4 over 0, 4 above 0, and remember the formula, again, for the n and the r, is the n factorial over the r factorial over the n minus r factorial. So that's where the formula comes in. So for the first one here, this one's going to be 4 factorial over 0 factorial times 4 factorial. And this will be x to the 4th, and of course 2 to the 0 power is just 1, so it kind of disappears. Plus, the next one is going to be, so we're working on this one, 4 factorial over 1 factorial times 4 minus 1 factorial, which is 3 factorial, x cubed times 2 plus, so now we're here, 4 factorial over 2 factorial over 4 minus 2 factorial, which is 2. That'll be x squared, and 2 squared is 4, plus, so now we're here, 4 factorial over 3 factorial, 4 minus 3, 1 factorial, which is x times 2 cubed, which is 8, and then plus the very last one here, which is 4 factorial, or 4 above 4, which is going to be, if you kind of actually write this out, it's actually going to be the same thing as we've had before, because 4 factorial over 4 factorial over 4 minus 4 factorial, which is 0. X to the 4 minus 4 is going to be x to the 0 power, which is going to disappear, and then you're left with 2 to the 4th power, which is 16. So finishing this out, or let's say reducing it, what happens here is the 4 factorial cancels out the 4 factorial. Remember earlier we defined 0 factorial as a special case. It's actually equal to 1. So that leaves me with 1 x to the 4th plus. Over here we end up with 4 factorial over 3 factorial. So that's going to be 4 times 3 times 2 times 1 over 3 times 2 times 1. And the 3's, the 2's, the 1's cancel, and I'm still left with x cubed times 2 there, plus, now 4 factorial again, over 2 times 1 factorial times 2 times 1 times 4x squared. What happens here is the 2's cancel, and we'll be able to finish that one out, plus, now here we end up with 4 factorial over 3 factorial, which is going to give me the same thing that I have here, like looking for shortcuts. So that's going to just end up with 4 times x times 8. And then same thing on the last one. All of this reduces to 1. That reduces to 1. So all you have left here at the end is plus 16. So now going back through and reducing this one more time, we have x to the 4th plus, all you have left here is 4 times 2 times x cubed, which gives me 8x cubed. All you have left up here is, you can actually reduce, say, this 4 and this 2 to 2. That leaves me 12 times 2, which gives me 24 x squared, plus 32x plus 16. And if you take that answer and compare it to what we just got, we got same thing, x to the 4th, 8x cubed, 24x squared, 32x, and 16. And that is how you use that formula for binomial expansion. So you have 3 options now for binomial expansion. You can actually full it out. You can use the formula, which is here. You can use the binomial coefficient idea and this idea of factorials to expand it out. And or you can use the pattern that we can develop from each sequential power, from, you know, squaring something to cubing something, the 4th power, and so forth. Okay, so practice using those formulas. And the last thing that we have in this section is, if I just want to find a particular term of a binomial expansion, if I just want to find the first term or the third term or the 5th term, we do have a way that we can also do that. Of course, the pattern was, the first term was, of course, the r was 0, the second term is when the r is 1, the third term is when the r is 2, and so forth. So again, you can kind of almost jump right to just a particular term of the expansion. So the r plus 1, or the r plus first term of the expansion, is n above r times a to the n minus r br. So the formula is the exact same as the binomial expansion. But the difference here is understanding this r plus 1. This r plus 1 term right here. So to show you what I mean on that, and how that's applied to this formula is on this one, they want me to find the fourth term in this expansion. So the way we know how to set that up is the fourth term comes from r plus 1. And the way we know that is, again, the first term is the 0, where r is 0. Second term is where r is 1. Third term is where r is 2. So it's always, if the r is 2, if I add 1 to that, that means I'm getting the third term, if that makes sense. If I'm using r equals 1, if I add 1 to that, that means I'm getting the second term. So depending on the r, if we add 1 to it, that's how we know which term we're looking at. So the next one over here would be n over 3 to the a, n minus 3 to the b third, and that would be the fourth term because the r is 3. You add 1. So that's where that idea is coming from. So if I'm wanting the fourth term, 4, since that's equal to 3 plus 1, that means, therefore, my fourth term is going to be the 3 plus first term. So that's how I know what I'm actually using. So I'm using this 3 plus this 1. So knowing that means that my r is 3, because that's where the r comes from. That's the first number. My r is 3. My a. Now the a just goes back to, this is what we have. This is my a plus b to the nth power. So everything else is given to me. My a is going to be 3x. My b is going to be 2y. And of course my n is 7. So those are the numbers that I use to find just the fourth term. I don't have to plug in and start with 0 and then go to 1 and then 2 and then 3 and then 4. Using this r plus 1 will take me right to the term that I need. So to plug this in, of course, again, the formula is n over r, n above r, times a to the n minus r, b to the r. So on this one, I'm going to have n is 7, r is 3, a is 3x to the n minus r, which is 3 power, times the b, which is 2y, raised to the r power, which is 3. So we've got the b to the third power, the a to the n minus r power, and now we're ready to just work just this one. Again, remember that's n factorial over r factorial times n minus r factorial. So, of course, that's going to give me 7 factorial over 3 factorial times 4 factorial. Of course, that's going to be times 3x. That will be to the 4th power times 2y to the 3rd power. 7 factorial is going to be 7 times 6 times 5 times 4 factorial. And that's going to be 3 times 2 times 1 times 4 factorial. Of course, times, go ahead and we'll go ahead and do the rules of exponents here. 3 to the 4th power is 81, x to the 4th power. And then here this will be 8y cubed. So finish this problem out. The 4's cancel. We can say this 3 and this 2 cancels out the 6. So that's going to leave me with, all I have left here is 35 times 81 x to the 4th times 8y cubed. And 35 times 81 times 8 will give me 22,680 x to the 4th y cubed. So there are a couple concepts of how we can expand out a binomial raised to a pretty high power, a squared, a cube, things like that, without having to actually just FOIL continuously. It's going to take work regardless of what method that you use. These are just, there is some time that's going to be consumed when you're going to expand something like this. But the larger you go, I think you'll find that the binomial expansion will actually serve you as a little bit of a shortcut versus having to FOIL continuously and have a long, big, expanded problem.